Hello, this is Team CH4. Welcome to our design review for the 2026 Build a CubeSat Challenge. I'm Aiden.
I'm Zaray.
I'm Christos.
And I'm Karan.
So our mission statement is to examine meteorite impacts on the moon's south pole and to determine and analyze the frequency of meteorite impact for future moon bases for 3 years. This mission will be conducted using a 1U CubeSat with a camera and Raspberry Pi. All the materials in the CubeSat will be mentioned later in the mass budget and the bill of materials. The CubeSat will examine meteorite impacts and determine and analyze the frequency of meteor impact on the lunar surface. This mission will be conducted over the course of 3 years, and it will be mostly conducted in the lunar South Pole region, specifically at 9 possible locations for the Artemis landing site. As the CubeSat is orbiting around the moon, which we will go in detail in our general orbit information, it will take pictures of the landing sites. As for how, our CubeSat will mainly image the surface of the moon to detect new craters, but the CubeSat will also be on the lookout for detecting infrared flashes that the meteorites emit when they hit the moon.
These are our SMART goals for our mission statement. Our specific goal for the mission statement is that while in low lunar orbit, the satellite shall map the frequency of meteor impacts on the south pole of the moon. Next, our measurable goal is the CubeSat shall take 3 pictures of the lunar surface every time a satellite orbits over the south pole. The attainable goal is the CubeSat shall utilize micrometeor flash analysis or crater analysis to determine impacts. Our relevant goal for the statement is that the CubeSat shall map the frequency of meteor impacts, shall allow the future lunar bases to access their risk of impact. The time-bound goal is the CubeSat shall map the frequency of these meteor impacts for 3 years. The following subsystems' SMART goals shall be tested by themselves or be tested in conjunction to achieve these goals. As for SMART goals for communications, CubeSat shall use an antenna to send pictures between 3 ground stations in DSN. We chose to use DSN because there was a multitude of documentation available on it. Furthermore, it is relatively powerful compared to other networks besides its downsides. The CubeSat shall send pictures no slower than 1 image every 120 seconds while data uplink is available. The CubeSat shall use lossless compression to compress the images before sending. Because we compress using lossless compression, no image data is lost, while is especially important since our GSD is on the higher side despite the reduced compression. The CubeSat shall do this in order to send the results back to the ground station, helping gather data on lunar terrain, especially craters, for upcoming Artemis missions. In addition, the CubeSat shall send images for the entire duration of the 3-year mission. As for our verification for communications, the link shall be tested for closure on ground.
The power shall be increased when the CubeSat is facing the sun, and when it is around the sun, it shall be fully covered from any light. The battery in the CubeSat shall let this system run for 3 years, and the battery level shall not fall below 10%. The CubeSat shall be powered via light incoming from the sun, using the solar panels. Without enough power, or being in the eclipse for too long, it will cause the CubeSat to not be able to send data of the frequency of meteor impacts back into the ground station. The CubeSat shall remain in power for 3 years, and the CubeSat's USB power meter shall go from 0% battery to 100% battery, solely using the solar panels and the sunlight.
The CubeSat shall take photos frame to frame to image the South Pole. The CubeSat shall have a GSD, which is the real-life distance between the center of 2 adjacent pixels of 50 meters or less. The CubeSat shall take pictures from the Raspberry Pi camera and compare images of the South Pole to analyze the frequency of impacts on the South Pole. The CubeSat shall be tested to take a picture upon a command, and the GSD shall be calculated using the camera and altitude.
At the start of our launch, we test all onboard system on the CubeSat for health. We do the same at the start of orbit, and if it succeeds, we move on to the orbital phase. When we are orbiting the moon, the CubeSat will take end-to-end pictures on the Artemis area of interest on the south pole of the moon. The CubeSat may also watch for flashes on the moon caused by impacting craters and send any data it finds to Earth.
As explained before, our operation site is near the south pole of the moon. The reason why we did not use the NRHO eccentric orbit was because we were concerned that the CubeSat would go too fast, which affects image quality. We achieved our orbit through a paper by the AIAA that lists multiple orbits that are the most stable in a 3-year period. And we found an orbit from the paper that suits our LLO nearly circular orbit. After we settled on the orbit, we ran simulations and other tests on SDK to verify that it could stay in the orbit for 3 years.
Our CubeSat as a system is relatively simple, consisting of a Raspberry Pi at the heart and command and data handle connecting to an IMU, antenna, and camera. The power subsystem that makes it go consists of a solar panel, a controller for it, and a battery to hold charge for eclipses.
As for software, the CubeSat is mainly active over the South Pole. We only do imagery while over the South Pole to conserve resources for data downlink, and to have enough resource to do imagery over the South Pole.
We shall develop our software in this order, in accordance with our integration and test plan. Our plan is to develop software in parallel with this priority in mind. Micrometeor analysis is a secondary goal, and will be explained in a later slide.
We will use a team organization system based on a task board on which work is divided. Tasks are written in cards to which a person can be assigned to with a limit of 2 tasks per person at any one time. A card consists of a title, description, requirements, a slot for someone to be assigned to, and dependencies. In terms of hardware and software integration within each other, we will test subsystems together and integrate them as necessary near the end of development, with each subsystem being tested individually in accordance with the task board.
Meteor impact flashes are brief events that occur sparsely on the lunar surface when a small meteor collides and produces light dependent upon its composition. Here, in this visualization, depicting camera detection of meteor impact flashes, the camera pixels are created, or optimized, to detect light in the visible spectrum. Since the bulk of the light generated by the meteor impact is inside of the visible spectrum, these can be likely detected under the right lighting conditions. Additionally, since the wavelength of the flash depends on the composition of the meteor, we can also estimate the material it was made out of.
Here is the mass budget and bill of materials. Our main expenses above are the Raspberry Pi 4B and the Raspberry Pi camera module and the SD card.
In addition to the 3 items in the previous slide, the Pi sugar also contributed a lot in the total cost of materials.
Here is more of the mass budget and the bill of materials, including the solar panel.
Here is the rest of the mass budget and bill of materials. The total cost of the CubeSat itself was $249.68 at a weight of 468.72 grams. The final total of every material we used is $309.98.
In our power budget, according to the battery descriptions, the battery has a charge of 5,000 milliamp hours, our 18.5 watt hours of charge. We got the 11-hour charging figure by dividing the capacity over the wattage. Additionally, our positive power margin, meaning that our production exceeds our consumption, lets our battery keep a healthy charge, ensuring the battery never gets too low. We use the solar power generation equation to get a power generation of 1.361 watts in full sun. The power generation is higher than listed on the datasheet due to the lack of an atmosphere in lunar orbit.
If we put the OS in hibernation or special software state, we could achieve an estimated 0.4 watts during the inactive part of the journey. During the active span, the CubeSat power consumption is approximately 10.25 watts, taken from the 3 major components. The CubeSat shall be going over the South Pole around only 3% of the time, so doing some math on the averages approximates to be 0.73 watts on average. Using the depth of charge formula, we concluded that the battery depth of charge is 3.4%, meaning that only 3.4% of the total battery capacity has been removed per eclipse on average, and we can use 96.6% of the battery. This gives us plenty of room to weather longer eclipses.
Our 3 ground stations are DSS 34 at Canberra, Australia, DSS 54 at Madrid, Spain, and DSS 24 at Goldstone, USA, giving a broad range of coverage.
We selected the lowest S-band frequency for our uplink frequency because it is a more power-friendly option while still being in the S-band range for the ground stations to pick up. The antenna diameter was on the ground station website. The aperture efficiency we figured out using the gain to aperture formula. Similarly, we used a mathematical formula for the uplink antenna power at the feed and the satellite uplink G to T ratio in decibels per Kelvin. For bandwidth, we started at the max bandwidth and decreased it until the uplink carrier to noise ratio was positive and the bandwidth was compatible. And we compared the link budget at different parts of the orbit. Non-duplexed means that it does not send data at the same time as it receives data.
Similar to the uplink, we use similar methods to find the downlink values. We use the link budget calculator online for both the uplink and the downlink.
Here is the data budget. The raw image data per image is 14.24 megabytes. This is based on the camera resolution and color values. Raw data of one image is multiplied by the number of pictures to get the total raw image data. Out of a total storage of 32 gigabytes, only 21 to 20 gigabytes can be stored due to the other data already stored on board for it to run, such as the operating system and code data.
In order to send the images back from Earth, we shall use a zip file compression system using a 25% to 50% compression. After compression, we can fit 1,872 pictures, but we round down to 1,800 for safety. From our link budget, we have a downlink data rate of 0.144 megabytes per second, so it shall take 74.2 seconds to transmit one image, and with overhead, this becomes approximately 90 seconds. For uplink, we have 212 kilobytes per second data rate, which is sufficient for command and housekeeping traffic, as these may only be a few kilobytes.
Thank you for listening.